There's two questions here in Laplace's equation. The second one probably being more relevant because this is more of an exercise. Kind of setting you up for lab 7 of the VBA. So we got a square plate. I don't know how well I can draw. Allow me a line here. It really should be a square. More like it. And I want to mesh this up. No. So I want to mesh this up. What does it? Okay, we've got these temperatures around it. The left temperature is 10. The right temperature is 20. The bottom temperature is 120, and that's the whole way across the boundary, and the top temperature is 0. Steady state is given this. Mesh the plate into squares so that there are 4 internal nodes. So that if I do this, they're supposed to be squares. I have 4 internal nodes. Use finite differences or the mean value property to write down an equation for each node. So I think I will, well, the second question, so using finite differences to get the mean value property is the next question. So I'll leave that there. So the temperatures I have, I can call them whatever I want. Now you can just call them temperature 1, temperature 2, temperature 3. That's absolutely fine. That's, I think, what I'll do here. Temperature 1, obviously for if you've got a finer mesh and you're printing it, you want to do better than this, but this will do. And then after this is really, really simple. It's just, so what's called the mean value property says that, say, for example, temperature 1 is the average temperature across around this circle. And if you, that's the mean value property. If you approximate the mean value property by just saying, let's average the 4 known temperatures, 1, 2, 3, 4. And if you, in fact, approximate the Laplace equation using finite differences, you'll be led to that conclusion anyway. So let's see how that goes. So there's just going to be 4 little equations here, very, very easy. Anyone who's done lab 7 will see this. So temperature 1. So what are the 4 adjacent? So above you've got temperature 4. To the right you've got temperature 2. To the bottom you have 120. Now specifically I'm talking about this node here, but both of these are 120. Both of these are 20. Both of these are 0. Both of these are 10. So plus 110, 120 plus 10 divided by 4. And do it for the 4 of them. Temperature 2 is, so above I see T3, to the left I see temperature 1, to the right I see 20, and down below I see 120 divided by 4. Temperature 3 I see, say below is temperature 2, to the left is temperature 4. And above temperature 3 is 0, to the right of temperature 3 is 20, divided by 4. And finally temperature 4, I see temperature 1 below, temperature 3 to the right, temperature 10 to the left, and temperature 0 above. So it's really just preparation for lab 7 more than something that you'll get. Okay, so what we want to say, the discrete mean value property is what we just used above, and we want to derive that using finite differences. So the first thing we have to do is kind of set up a point on a plate. So all the points in the plate, you'll notice, have 4 neighbors. So we can just generically do that. So take a point here, that's our temperature, and you got a temperature above, temperature to the right, temperature below, and temperature to the left. Now this should be done in such a way that it's a square mesh. So this would be delta x, this would be delta y. Delta x is equal to delta y. Now the clever thing to do here is, well, you can label it however you want. I mean, all I want to say is that this temperature in the middle is the average of the other 4. So you can call them whatever you want. I mean, I like maybe temperature right. Does that confuse with something up here? Maybe it does a little bit. So maybe we'll call them, and even it'll confuse a little bit above. So maybe we'll call this one temperature I. Doesn't really matter. Let's just call them temperature 1, temperature 2, temperature 3, temperature 4. Now we have to understand this is with respect to an axis x and y, And with respect to that axis, this is next temperature with respect to x. So you're talking about at this point, the next one is T1 and the previous one is T3. And temperature here is the current, and it's the current with respect to x and with respect to y, because if you go up, this is the next with respect to y, and then this is the previous with respect to y. And the finite differences, well, look up the top of the page there, we're dealing with second derivatives, so we want to find the finite differences for second derivatives. So let's go to the back of your written assessment and go and get that formula. So this is the formula that we want to approximate second derivatives. And note this I plus 1 means at the next x point, and the x could be x or y. So this is next, this is current, and this is previous. And I'm going to write down Laplace's equation. It says the second derivative, partial derivative of temperature with respect to x plus the second partial derivative of temperature with respect to y is equal to 0. And we're going to approximate both those second derivatives using our schematic above and that finite difference thing there. So Laplace's equation implies approximately, so let's do the derivative with respect to x first. So note that with a partial derivative you don't change in the y direction, and temperature 3, t and temperature 1 all have the same y coordinate. So when you're doing next, current and previous for this derivative here, this is going to be next, this is current, this is previous. So the next temperature in terms of x, so this basically, this xi means this point here. So the next one minus twice the current plus the previous. So the next temperature here is temperature 1 minus twice the current is temperature T plus the previous temperature 3, and then the delta x then is the distance between them, which in this case is also delta x. Now do the same trick for the y direction. So we're approximating now the second derivative with respect to y. So the next temperature with respect to y is temperature 2 minus twice the current is T plus the previous with respect to y is temperature 4. So you got to understand we are approximating these second derivatives at this point here. Now the delta x is the distance between those points, which is delta y equal to 0. But we've assumed delta x equal to delta y, so we can multiply both sides here by delta x squared. So you're multiplying delta x squared by a sum, you have to multiply them both by delta x squared. When you multiply the first term by delta x squared, the multiplying by delta x squared gets rid of the division by delta x squared, and you just have t1 minus t2 plus t3. And then when you multiply the second term by delta x all squared, the fact that in fact delta x is equal to delta y means that delta x squared multiplying by delta x squared gets rid of the division by delta y squared, because they're the same thing. And so if you get rid of that division, you're talking t2 minus twice t plus t4 equal to 0. And what we want to show is that the temperature at a point, so that's what we're calling t, is the mean or the average of the temperature at the adjacent nodes. So we're trying to show that t is equal to the average of t1, t2, t3, t4. And that's not difficult here. You can just add 4t to both sides. And I'm just swapping right and left. If b is equal to a is equal to b. So I could imagine I have 4t on the right hand side, but I can also just say right hand side equal to left hand side. And on the other side of t1 plus t2 plus t3 plus t4. In other words, the sum of the adjacent nodes. So if I finally divide by 4, I'm good. So divide both sides by 4, I get the temperature is t1 plus t2 plus t3 plus t4 divided by 4. In other words, the mean temperature at adjacent. Very good.